All right, looking at practice HL paper 1 here. Somebody asked me about number 7. So we have a big old nasty fourth degree equation, and we know that we're talking about complex numbers, and we're only told 2 of the roots, and that means that there's 2 other roots here. So there's a couple things that you need to know to answer this kind of question. You need to know what happens when you multiply out roots, and what happens when you have a complex root. Okay, so here's one of the ideas. And this idea comes from the quadratic equation. That's one way, at least, to think about it. If you think about the quadratic formula, I should say, you have something that looks like this. And if I get a complex number, what that means is that this chunk right here is negative. The stuff under the square root is negative. And what that means is that if x is equal to a complex number, so I'm just going to use letters I haven't used before. So if x is equal to, let's just say, a real part plus an imaginary part, then notice that our quadratic formula had a plus or minus in it. So if one of our answers is a real part plus an imaginary part, then our other answer has to be a real part minus an imaginary part. So this is true whenever you're solving a equation that has real numbered coefficients. This whole logic breaks down if the a's or b's or c's are allowed to be complex numbers. But because here we have real numbered coefficients, we know that if one of our roots is complex, then we have to have its conjugate as a root as well. So I know that a plus bi and b plus ai are roots, so I also know that a minus bi and b minus ai are also roots. Now, here's the other thing I know. I know that if you have a polynomial, you can factor it. Once you know all of its roots, you can factor it. So if the beginning thing equals 0, then I know that z minus a plus bi and z minus a minus bi, missing one there, and then z minus b plus ai and z minus b minus ai. I know that this has to equal 0, but I also know that it needs to match up with all the original bits. And I'm not going to multiply all this out because that just sounds like a lot. I'm just going to multiply out the easiest parts to multiply out. So for example, I know that the only way to get the number 400, which has none of the z's on it, the only way to get that is to go each of the roots multiplied together. And there's 4 negatives being multiplied, so I can ignore those. So what I know is that a plus bi times a minus bi times b plus ai times b minus ai all has to equal 400. If you multiply out the first 2 chunks, you get a squared plus abi minus abi and then minus b squared I squared. And that simplifies because the abi and the minus abi cancel out. So I can follow that same pattern on the other one. I know my abi is going to cancel out, so I'm really just going to have b squared minus a squared I squared. And that's still going to equal 400. Well, I squared is equal to negative 1, so what we have is a squared plus b squared times b squared plus a squared is 400. But those are actually the same term. So I have a squared plus b squared times itself makes 400. Which means if I take the square root, a squared plus b squared is either positive or negative 20. We know it has to be positive because a and b are integers there. A and b are not complex numbers. So when you square them, they're going to be positive numbers. So now we have this great conclusion. A squared plus b squared equals 20. And I know that just from thinking about how could I multiply out the factored form and match it up with 400. Okay. Next, you could try to think about, there's a couple different ways. You could try to think about how could you achieve the 4 here, or how could you achieve the 80 over here. You should get the same result either way. I would suggest trying to attack the 4, because if you attack the 80, you're asking yourself how to multiply 3 of the non-z's times the fourth z. And there's 4 different ways you can do that, and you still need to multiply out 3 of the different roots. So that sounds like it sucks. But if I want to make a z cubed term, the only way to make a z cubed term is to go z times z times z times not z. So there's 4 different ways that you can do that. And each of those ways involves one of our roots. But there's an extra negative involved. So here's how it turns out. We know that 4 has to equal the opposite of a plus bi plus a minus bi plus b plus ai plus b minus ai. So think about how that works. If I multiply the last 4 z's, then I have a plus bi as the coefficient of z cubed. If I multiply the first times the third times the fourth, that gives me a minus bi. If I go 1 times 2 times 4, I get this, and if I do 1 times 2 times 3, I get this. But they're all negative. So if I simplify that, I get 4 equals negative. Positive and negative bi cancel. Positive and negative ai cancel. A plus a, b plus b. Simplifying, I can divide everything by negative 2. So I have negative 2 equals a plus b. So now I have two things. A squared plus b squared equals 20, and a plus b equals negative 2. I'm just going to create this into a substitution, just that negative 2 minus b is a. Substitute that into my other equation. I don't know if we'll be able to fit it. We'll try to fit it down here. Negative 2 minus b squared plus b squared equals 20. If you distribute out that, you get 4 plus 4b plus b squared plus another b squared equals 20. Everything's divisible by 2. Let's see if I can, maybe I'll slide you up here. Everything's divisible by 2. So I have 2 plus 2b plus b squared equals 10, because I divided by 2. Get everything in order. B squared plus 2b minus 8 equals 0. B plus 4, b minus 2 equals 0. So my two options are b equals negative 4 or b equals positive 2, which define my two a values also. A could equal positive 2 or a could equal negative 4, because those are the values that make sense with this substitution right there. And so that's my answer. So that's one way you could approach this problem. You really could multiply everything out and equate each of the coefficients, but you, in general, you only really need to look at the constant term and the n minus 1 term. If you look in your formula packet, those are called the sums and products of roots, or they're called Vieta's formulas. So let me know if you need any help with that.